fluid dynamics. First we have Bernoulli's equation. Bernoulli's equation is pressure 1 by rho g plus v1 square by 2g plus z1 is equal to p2 by rho g plus v2 square by 2g plus z2, where z1 and z2 are heights and rho is density. And from continuity equation, area 1 into v1 would be equal to area 2 into v2, or d1 square. Here d1 is diameter square of first surface into v1 is equal to d2 square into v2. And angular momentum conservation, for angular momentum conservation we have mass into velocity into distance is equal to some constant. Delta mvr is 0. And so if we have a body and it is flowing, its fluid velocity, some fluid is flowing past it with v1 velocity, v1 is fluid velocity, and w is the distance of the body. So our actual velocity would be v1, which is fluid velocity, plus w, which is the distance or distance of the body, or we can say it is also angular velocity, which is given in radian per second. Then mass is density into mass flow rate, so m would be rho into q. So rho, which is density, would be mg by area. Mass flow rate would be equal to area into velocity. Q would be equal to mass flow rate is area into velocity. So m would be equal to rho into area into velocity. Next we have horizontal velocity v given as root 2 gh. Then momentum equation. Momentum equation states that force, which is which is rate of change of momentum, is equal to m delta v. Then we have Prandtl tube or pitot tube. So for this, velocity is c under root 2 gh, where h is head of stagnation point, and h is also equal to differential manometer reading into rho m, which is manometric fluid density, by rho w. This basically is relative density because we are dividing it by density of water, so this is relative density minus 1. And incompressible forced vortex flow, it is shear stress 0 at all points in flow, vorticity is present, and w is constant, which is equal to v by r. Therefore v is directly proportional to r, which is velocity is directly proportional to the radius of the body. And forced vortex means no Bernoulli equation is applied in that case, as total mechanical energy is not constant, as there is loss to irrotational flow. Next we have is flow through pipe. First in flow through pipe we have is losses through pipe. Losses could be due to friction, expansion, compression, entry loss, exit loss, pipe bend loss. Major losses are one of the major losses, head loss due to friction, and it is given by Darcy-Weisbach equation, which is HF, this F being the friction factor. So HF would be, head loss due to friction factor is F into L into V square by 2 GD. F we have already stated is friction factor, and HF is equal to 4F dash LV square by 2 GD. F dash is fanning factor or coefficient of friction. 4F dash is equal to F. Coefficient of friction 4 times is equal to friction factor. And F is equal to 64 by RE for laminar and fully developed flow. So if we put F is equal to 64 by RE in this equation, we get HF is equal to FL. Sorry, this is other equation. So if we would put F into this equation, we would get equation for laminar and fully developed flow. Then HF is equal to FL Q square by 12 T to the power 5. It is in terms of discharge, and Q is given in meter cube per second. Then we have fully developed laminar flow in pipe. Before that, there are few formulas. For laminar flow, tau is minus del P by del R into R by 2. And for wall shear stress, tau W is minus del P by del R into R by 2. And for flat plate, diameter is 4 times of area by perimeter, and tau W is mu du by dy. And for fully developed laminar flow in pipe, delta P is pressure drop is P1 minus P2, and there is no variation in velocity profile in this case. So basically this is a pipe and this is the velocity profile. So there is no variation in velocity profile. So pressure drop is P1 minus P2, which would be equal to 32 times of mu VL by d square. L is the length of pipe and d is diameter. And in case of Reynolds number, if this for fully developed flow, we would use this formula, and for that case we know that Reynolds number is less than equal to 2000, so it would be a fully developed. And for fully developed flow, and for laminar flow, we know that RE is less than 2000. And tau W is del P, which is pressure drop into D, diameter, by 4 times of L. So head loss due to friction would be pressure drop by rho G, which is equal to 32 mu VL by rho G d square. Then we have case for pipes in series and pipes in parallel. So in case of pipes in series, HL being head loss increases, and in case of pipes in parallel, discharges increased, and Q remains the same in case of series, and this is at constant head in case of parallel. So HL, which is total head loss, is given as HL1 plus HL2 plus HL3, and Dupin's equation for pipe in series is L equivalent length by equivalent diameter to the power 5 is equal to L1 by D1 to the power 5 plus L2 by D2 to the power 5, and so on. And in case of parallel flow, we have Q, total Q would be equal to Q1 plus Q2 plus Q3. Like supposedly this is a pipe and flow is taking place and these are two parallel pipes, so this Q would be equal to sum of all the parallel pipes. So Q would be Q1 plus Q2 plus, and so on. Then our equivalent diameter would be equal to n to the power 2 by 5 into d, where n is number of pipes in parallel connection and d is same diameter of individual pipe. This is diameter of individual pipe. This case is valid for if the diameter of all the pipes are same. So to calculate d equivalent to the power 5 by L equivalent under root would be equal to d1 by L1, d1 to the power 5 by L1 under root plus d2 to the power 5 by L2 under root, and till n number of pipes. Next is power transmission through pipe, which is calculated as rho G Q into head loss due to friction. Velocity is given as Q by area. HF, all the formulas we have already studied, which is HF is equal to FLV square by 2GD, or it is equal to FLQ square by 12D to the power 5, or it is equal to 4F dash LV square by 2GD, or in case of laminar flow it is equal to 32 mu VL by rho GD square. And maximum power is HF is equal to H by 3, which is capital H being net head. Then we have Bernoulli equation for real fluid, which is P1 by rho G plus V1 square by 2G plus Z1 is equal to P2 by rho G plus V2 square by 2G plus HL, total head losses. And taking this to the other side, pressure to the other side, we get P2 by rho G plus Z2 minus this Z2 is also there. So P2 by rho g plus Z2 minus of P1 by rho g plus Z1 would be equal to V1 square by 2g minus V2 square by 2g minus head loss. And this is basically, this side is difference in physiometric head. And sudden expansion loss is given as He would be equal to V1 minus V2 whole square by 2g. And we would study question on this example as well. Like if we have two flows are submerging into one and density of this is given as rho 1, area as A1 and volume as V1, and for this pipe density is rho 2, area A2, volume V2, and total submerged pipe flow density is rho 3, area A3, volume V3. So in this case rho 1 A1 V1 plus rho 2 A2 V2 would be equal to rho 3 A3 V3, and mass flow rate of pipe 1 M1 dot and mass flow rate for pipe 2, sum of these would be equal to mass flow rate for pipe 3. This is pipe 1, pipe 2 and pipe 3.